we're here. Okay, so yeah, so I'm gonna have to amend the homework that is due on 10/7. So because the exam is 10/5, right? So it's on the 5th. So it's next week on Tuesday. And I don't currently have a classroom. If I'm not able to get a classroom by Thursday, by next class, then we'll do it online, in which case you guys are going to need to find a mirror because I'm going to need to be able to see your screen. I've had a lot of students complain to me about the online proctoring options, which I actually think the online proctoring options are fine, but I've never had to take one like that. I don't know if the people who are complaining to me about it were complaining because they want to cheat or if they're complaining because actually the online proctoring options are pain. I assume I probably got some of both. But there were a lot of complaints, even though I never even used it, but people were still complaining about it. So anyway, so I'm going to, regardless, I need to find a classroom. If I can't find a classroom, we'll do it online, but I'll need you to have a mirror behind your setup so that I can make sure that you're not using your internet to cheat. Okay, so other than that, let's see here. We've got, so the homework that is due on Thursday, I'm going to push back to Sunday. I had a request from somebody who was swamped with homework. So I'm going to push that back. So it was due Thursday, and I'm going to push it back from 9:30, which is Thursday, to whatever Sunday is. That's probably like the 1st of October, or what is Sunday? Oh no, Sunday's the 3rd. Okay, I mean, I haven't done it yet, but I'll go in there and I'll change that. Okay, so any questions on that? Other than that, the homework for the following week, if you've already started it, then I'll have to, like, I don't know. I haven't even taught you the material for it yet, but the following week, which is due on the 7th, I'm gonna at the very least push that back. I might change it entirely. It's gonna cover some stuff that we're doing now. The exam next week will cover everything prior to this class. Okay, so it is not. So on the schedule, it says that we're doing reactions right now. We're not exactly doing reactions. We're going to do equivalent systems today. But, we'll do equivalent systems, which is like it's kind of like the precursor to reactions. So yeah, let me let me write all this down because that's a lot of stuff. Okay, so homework / connect due on Thursday. It's Thursday on the 30th, I think. That's being moved to the 3rd. Okay, it's moving from Thursday to Sunday. I had a request for that. And then the homework 5, connect 5, due on the 7th. Okay, don't start that yet. Okay, gonna move. Okay, and then the exam is on the 5th. Okay, so that's next Tuesday. So that's a week from today. Okay, and it's going to cover everything up to, but not including today. Okay, so yeah, so basically, like, if you want to review, go into, there's a lot of ways you can review. One is you can go look at the old tests, which are on Moodle. These are my old tests. Another way is you can look at that link that I sent with a bunch of old tests that somebody else put up there. They don't necessarily cover the exact same material, but you can look at it and say, oh yeah, that's something that we've covered. And then I've created a whole bunch of practice sets, which is, it's basically your homework problems plus a few other problems from each chapter so that you can, study that. So that's what you should do. And that's what I recommend. And obviously, if you need me, I'm always available during office hours. So you can always find me. Okay, so any questions?
Exams all closed notes and everything, right?
I'm going to give you, so if you go, and I don't think you should need this, but it will be attached. So if you go under resources, under Moodle, there's an FE handbook, which is the handbook for the entire FE. And then there's one called the FE statics equations, which is basically like I cut the pages out of the FE handbook that pertain to statics. And I'm going to give you that. My guess is on this particular test, you won't need any of that, but make sure, and as I highly recommend, I recommend you have that printed out and you just keep it in front of you and you stare at it so you understand that this is the way the information is going to be presented when you take the FE. So that's what I'm going to give you. So I would, actually, I guess, how am I going to give that? I guess I'm just going to, attach it to the back of the test. So everybody's going to have an extra, it looks like 4 pages, 2 of which are just information about shapes. The other ones, the risk is what a lot of people do is without understanding the equations as written in the statics thing, they'll be like, okay, I'm stuck. I know this is, say, a centroid problem. I know this is a resultant problem. I know whatever. And they just start, copying things out of this thing, and they don't understand what any of these things mean. And so, they miss problems. So that's why, my hope is so that you'll do that in my class and not on the FE, and then have to wait 6 months or a year. I don't know how often they give the FE before you can actually start working. So, I'd rather you get it, lose a letter grade in my class, or worse, or better yet, lose a letter grade on my exam. But, be okay for when you get out of here, because that's what this is all about. So,
Wait, so what's the exam? What chapters and sections is it on? Or it's just like,
can somebody answer that? Because I've said it 3 times already.
or like up to this class? Everything we did
Up to, but not including this class.
Or not including this class? Okay, thank you.
All right, yeah, sorry for getting testy. I just, I've said that a few times. Okay, so, all right, so any other questions? All right, so we are moving forward, and, it says that we're doing reactions, and it says that we basically got basically a full 2 weeks on reactions. We obviously don't, because one of those class periods will be used up with the test. But today will actually be on equivalent systems, and then we'll do reactions. And equivalent systems, is really just kind of like reactions light. Okay, we're not quite getting there. And so what this is a way to simplify a system.
Professor?
Yeah.
I'm sorry, I just want to be crystal clear about this. Up to moments and couples will be on the test.
What did we cover last class?
Moments and couples.
Okay, everything. Am I unclear? I'm not.
I just got a lot going on.
I'm just curious what it is about my language that's confusing y'all, because I want to fix it. I said everything up to, but not including this class.
That's clear. Thank you.
Okay, sorry. I know I'm being a little rude, but I feel like that's straightforward, but maybe it's not. Okay, all right. So just let me know. Like I know I'm being rude a little bit, but it does seem, I don't know. Okay, let me know. Okay. All right. So equivalent systems. So basically what we're going to do is we're going to take one system, and I actually don't even have a good example of one, but let's just imagine, I have a system that looks like this. Okay, I'll give you a really rough example here. Suppose I've got a bar, and I've got 40 newtons on this side, and I've got 20 newtons on this side. Okay, what I'm saying is, I want to take that and I want to replace it with something that's easier for me to think about, which is the exact same bar, but now it's only got a 20 Newton right here. Okay, and hopefully you can see that these are equivalent. Okay, they're not entirely equivalent. They're only equivalent if the system is rigid. Okay, so hopefully when you look at these two, you can see that, like in both of these cases, the net force is 20 to the left. Okay, but the only difference between these two is that this one's getting squeezed, right? This one's getting squeezed. Okay, and because it's getting squeezed, if it's not rigid, then clearly there's a difference between this one and this one, because this one will actually shrink a little bit, right? Like this one will actually get, it'll like shrink and be a little bit smaller because it'll be compressed under that squeezing force. Okay, so that's the way that these two are not equal, right? But in general, if rigid, then they are exactly the same. Okay, so what we're going to basically try to do in these cases is we're going to try to create a new system that is equivalent. And the goal of this, and I've thought about this a lot because I've never really thought about equivalent systems, moving through moving through my engineering education or whatever, like I don't really think about equivalences. I'd forgotten that this was a part of this course. And what I realized is that we use these, we create equivalent systems all the time. It's not necessarily the whole system. Usually there's parts of the system where we're like, you know what, this is complicated over there. I'm going to simplify it by doing these things. And these things are going to make my life a little bit easier. And so you just kind of start using this all the time in kind of little small ways. So what we're going to do is basically you're going to match between the systems. Okay, so what you're going to do is you're going to try to match. Okay, you're going to match the sum of the forces and the sum of the moments between the original and the, and the equivalent. Okay. And there's two things that they will ask you to do here. I say they because, these are the book problems. Okay. And it's not just this book, it's like all of the books. Okay. So there's basically two possibilities. Okay. One, you will be able to find equivalent system with force couple, with a single force couple at a given point. Okay, and then really it's just an extra step. You'll have to find an equivalent system with single force. And then you have to figure out the location. And then you need to find the location. Okay, and that's a little bit harder. And we're going to kind of treat this, basically like if you're asked this, if you're asked this second one, usually what you're going to do is you're going to do the first one, and then you're going to go from there to the second one. Okay, and I'll demonstrate that on some examples. Okay. All right. So there's basically, I don't want to say rules, but and I'm going to do this through examples, not through. This thing's so annoying. Okay. I'm going to do this through examples, and I'm not really going to do this through. I'm going to erase all of this. Okay. So I'm going to do this through examples and not through a lot of kind of wordiness and talking. But basically, it works like this. Okay, or what I'm going to say here real quick is this. Okay, forces, okay, on a rigid body. Okay, I'm trying to remind myself to say on a rigid body. This course assumes rigidity of the bodies. So you could like put that at the beginning of the chapter, I mean of the whole course. But I just want to make sure that years from now when you're like, I'm trying to remember how to do something, blah, 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 you just remember that that everything here applies on a rigid body. Okay, forces on a rigid body. Okay, you can always move. Can move along its line of action. Okay, with no change to the system. Okay, that's key. Okay, the second thing here is that you can move them off the line of action, but that will affect the moment. I guess I'll just say that will affect rotation. Okay, and so you'll have to account for that. So, I mean, just to give a real quick example before I even really get into this, let's imagine we had, a beam, right? And I've got a force up and I've got a force down. And let's say they're equal and opposite. Let's say this is, I don't know, 500 kips and this is 500 kips. Okay, and we've got a distance here of, I don't know, 20 feet, right? I'm just making this all up on the spot. Okay, I can, it should be noted that I can move that 500 on the top to the 500 on the bottom. And this is an equivalent system, right? I moved it along its line of action, right? So there was a dotted line here. That was the line of action of the force. And hopefully you've seen me do this enough that you realize that you just kind of like, I want you to internalize that you can do that. Okay. And so that's an equivalent system without changing anything else. The other thing I could do is I could say, well, the 500 up and the 500 down, well, they cancel each other out, right? So I could be like, oh, well, I'm going to draw an equivalent system right here. And those two are going to cancel each other out. Okay, but I think hopefully what you can see is that if those two cancel each other out, this is not an equivalent system. Like this right here is not equivalent to this over here. And the reason for that is because this thing wants to spin. Okay, so basically, like or forget the word cancel out, like if I took this 500 kip force and I just brought it over here, so I've got 500 up and 500 down in the same location, well, that's great. So now they're both gone, but I've moved this force off its line of action. Okay, and by doing so, in this case, I removed a rotation, right? So basically this thing wants to spin like this, and that is a moment, okay? And these two forces, this 500 kip and that 500 kip, have a moment. And if you remember correctly, I can like go right here in the middle, and I could try to get the moments for each of these forces, right? So I'm gonna put this moment right in here. And so maybe this force, okay, perpendicular distance is 10 feet. So this is gonna be 500 times 10 going, so this is gonna be 500 kips times 10 feet. Okay, and that's spinning clockwise, so that's a negative. Okay, and then we'll do the same thing with this one, 500 times 10. Okay, and so all told, we get 10,000. So this thing becomes 10,000 foot kips. So this would be 10,000 foot kips. Okay, and that would be the equivalent. This system right here would be equivalent to this system right here. Okay, this is all very informal. I'm about to do this a little bit more formally in a second, and hopefully it won't be so like kind of muddled. Any questions on that before I go and do something a little bit more formal with a real example?
Nope.
Okay. All right, so let's do like a real example. Is that right? Clear all drawings. Okay, good. Okay, so here's a real example. Where did I get this one? Oh, this one came from your textbook. I wish I remembered what number it was. I might even have assigned this one for homework, but it looks like this. I'm going to take a split second and give you a drawing. Yeah, or use my straight edge here, my trusty dusty straight edge. Okay, so we've got a force right here. And of course, if you were doing this in your textbook, it would, it's going to give you a different value for that force. I'm just going to give you 340 newtons. And then we'll do, let's say we've got like, I don't know. I'm just going to use the numbers on this particular problem. I'm going to add one thing to it, 400 newtons. Okay, and then down here, it's like this particular thing is like bolted in. Okay, onto like some kind of plate or something. All right. So, oh yeah, we need some distances here. This is going to be 150 millimeters. This is going to be also 150 millimeters. Let's make it 200 millimeters. I like it when my distances change a little bit so that you can follow the numbers if you need to. Let's make this one also 150 millimeters. Let's make it 160. And that way we can, again, so we can follow it. Okay, the last thing to do here, just because it's something that, I don't know, I feel like maybe it confuses people. So let's just, we're going to apply a moment right here. So right there at that dot right there at C, so it's going to be B, this is going to be C. I'm going to apply a moment. So what you can imagine is you can imagine at C, if I just took a screwdriver and put the screwdriver in at C and I twist it, right? So here we go. Right, and let's just say that that's 6 newtons times meters. Okay, so one of the ways you know that you have a So this is a little bit more complicated than the one the book gives you. Okay. And what we're going to do here, yeah, because the next problem does not have an applied moment. So this is a good one to have it. So what we're going to do here is we're going to create a few systems. Let's see here. So this is what's required. Okay. Determine the resultant. This is the language the book uses of the forces and moment, because there's a single moment there. And the distance from the ground to its line of action. Okay, so that's the language that they'll use. Or at least that's the language they use on this particular problem. All right, so what this is telling me really is what I'm going to do is I'm going to replace all of those forces and the moment, and I'm going to have an equivalent system. And usually I don't like to belabor the drawing of the equivalent system. Okay, but it's going to kind of like, it's going to look exactly the same. But it's going to have a single force. Okay, and I don't know if the force is going to be positive or negative, but it's going to have a single force. I don't know what to call that force. Let's just call it F. And it's going to be at a certain location. Okay, which I don't know what we could call it. We could call that Y, or whatever it might be. Let's just call it lowercase b. Okay, and so that's kind of what we're looking for. Okay, it turns out like it seems like I probably got the right force here. I'm a little bit worried about adding that moment in because that wasn't in the problem, but I guess we'll see what happens. Okay, so what we're going to do here is basically we're going to create an intermediate step. Okay, like I just said, like in the thing is that there's two things they're going to ask you for, and one is an equivalent force couple at a given location, and then the other one is a force couple at a given location. And then what they'll do is they can go from there to and then they can ask for a single force and for you to tell them the location. So what we're going to do here is here's the solution, right? So I want to look at this initial problem, and I want to look for the sum of the forces in the X. Okay, and I'm not going to set that equal to 0. I'm just going to expand that because I want to know what the sum of these forces is, because that's the equivalent effect that I need to have on any other system that I might use. So what I'm going to do here is I'm going to just add those forces up. So I've got, okay, so don't equal 0. It does not equal 0. I mean, it might end up being equal to 0, but it doesn't equal 0. So, just be careful there. The sum of the forces in the X. We're just looking for the net effect of all these forces. Okay, so that's 340 newtons to the right, minus 600 newtons to the left, minus 400 newtons to the left. Okay, so the sum of the forces in the X equals whatever that is. Okay, and here's my calculator. Okay, 340 minus 600 minus 400. I don't know why I'm doing this. I could do that in my head. Okay, but anyway, negative 660 newtons. Oh, by the way, I noticed that I feel bad about it. I was a little rude to the two of you who asked about what was on the test. I've been thinking about this while I've been doing this. When this is over, if anybody is unclear, let's talk about that. Okay, so just hang out. I won't be rude. I apologize. I get testy sometimes. I try not to, but so just my apologies. Okay, so so then we'll do sum of forces into Y. Okay, there are no forces into Y, so we're not even going to worry about that. Okay, so I chose this problem specifically because of that. Okay, because I didn't want to deal with forces into Y. Okay, so the next thing we want to do is I want to do the sum of the moments, because so whatever equivalent system I have, the sum of the forces in the X direction is going to be negative 660 newtons. In fact, I can go over here right now. I already know what the force is going to be. Right, it's 660 newtons to the left. Okay, I mean, I'm not going to go there because I just feel like that's kind of jumping the gun, but whatever. So I want to do the sum of the moments. And I need to pick a point that I want to do the moments around. Okay. And one of the things we haven't really talked about is these moments right here. And I guess I should have put this in the official notes. This moment right here, an applied moment can be moved anywhere with no questions asked. Like you can apply that 6 Newton times meters anywhere you want on this thing. It has the same effect. Okay. Now I know that that's going to be a little counterintuitive. I have a little video where a guy demonstrates that, and I'd like to show you guys that today. I guess we'll do that in a second, but we can just move that wherever we want. Okay, so considering that my ultimate question over here asks for a distance from the ground, distance from this point down here. So I'm going to do the sum of the moments around this point D. Okay, and again, like I almost wrote equals 0, does not equal 0. It equals whatever it equals. Okay, now because this thing is static, we know that ultimately it will be equals 0, but we're not, right now we're not accounting for the forces that are coming from that, that plate at the bottom, okay, and at D, okay, from those bolts and from being attached to the bottom. And we will get there, but we're just not there yet, okay, and that's what we call the reaction forces. So we're going to get there. So but I've just chosen point D. You don't have to choose point D. You can choose whatever point you want. I like D because my distances are pretty well defined. And I know, like, B over there, like this thing we're looking for, this thing is definitely going to be positive relative to point D. So, it's just like, I don't know, I just chose it. You could choose whatever you want. Anyway, so let's go ahead and see what we've got. And I'm going to do them. Well, let's start with the moment. I've got the moment. The moment goes directly into the moment equation. 6 newtons times meter. It does not need to be multiplied times the distance or anything like that. I do have to take care of the sign. So in this case, that is counterclockwise. So it's a negative sign. Okay. Now I need to deal with this 400. So now I need to deal with each force in turn. So I've got this 400 Newton force. Okay. And that one's causing things to spin clockwise. So it'll be plus 400 Newtons times this distance, which is 150 millimeters. I don't really like 150 millimeters. So I'm going to make that meters. Okay. And then so that takes care of that force. Now I'm going to do the 600 Newton force. 600 Newton force. Make rid of this. I don't like to have non-equations. 600 Newton force. Okay, and that's also going to cause things to go clockwise or counterclockwise, excuse me. So I'll put a positive sign on there. And its distance from D is 150 plus 200, so that's 350. Okay, and then the last force is that 340. Okay, we got 340 Newtons. And its total distance is 150 plus 200 plus 160. So what's that? 510. Okay, and it's causing things to go clockwise, minus. Okay, any questions about that before I continue? Because I know moments are new and you haven't done the homework yet. So.
Wait, where did the 350 come from? The 350 newtons.
So this 350 right here?
Oh, no, the newtons.
Oh, sorry, that should have been 340, right?
Oh, okay, yeah, it's 340 newtons, yeah.
Okay, yes, my apologies. Good catch. Okay, so then if I do some of the moments around D, I'll get a, let's see what we get here. So I get -6 plus 400 times 0.150 plus 600 times 0.35 minus 340 times 0.510. Okay, 90.6. 90.6. Okay, and notice the units here. The units here. This is newtons times meters. Newtons times meters. Okay, so what I've just done here, I'm going to plug that into my calculator again just to be sure. But is I've done that first type of problem already. Minus 340. 90.6. Okay, cool. So I've already done the first type of the problem. So I told you, I forgot what I called it, how I read it, but there's two types of problems they'll ask you. And one of them would be find an equivalent system with a force couple at a single point. This is a force and this is a couple. Okay, at a single point. In this case, I've done this at point D. Okay, so if the problem had asked you to solve for this and find an equivalent force couple at point D, then what you would do is you would stop right now and you would draw this. You go, okay, well, here's my equivalent system. Okay, and you're not going to belabor, all this too much, right? Maybe you're on a test or something, you've got a lot of stuff going on. So you're just going to draw the picture again, as rough as you can. And then you're going to, so here's point D. And so what you do is you'd say, okay, well, I've got Fx going this way. So this is 660 newtons. Okay, and the sum of the moments, the equivalent moment is 960 newtons times meters. Okay, and it's a positive, which means it's counterclockwise. And that's 90.6 newtons times meters. Okay, so that's where you would stop if the question were to find the equivalent moment force couple combo essentially at point D. Okay, now note we could have done this at a different point, and if we'd done this at a different point, this would have been an identical calculation. Of course, I got rid of that minus another 400. Forgot about that, or I erased it. But this one would have been different because these distances would have all been different. Okay, because instead of measuring it to D, we would have measured it to wherever you wanted the equivalent system. Okay, does that make sense?
Yeah.
Okay. So then the next thing we want to do is now basically I want to change. So this is equivalent. I don't know what is equivalent. Is that like 3 equal signs? Something like that. So now I want to do an equivalence over here. Okay. And hopefully you can see that like if I had 660 over here, like let's suppose this F, instead of being F, let's suppose it was 660 newtons. Okay. Hopefully you can see that. So let's call this system, I don't know, the second system. Let's call this system 2. We'll call this system 3. Okay. You can see that if B is the correct number, that because like what I'm doing is I'm taking that 660 and I'm moving it not along its line of action. I'm moving it up, right? It got moved from down here up somewhere. And so that has an effect on the moment. And I think hopefully you can see that this 660 right here imparts a moment around D. Okay, so that 660, if B is the correct number, if this number is correct, then I'm going to get the same moment around D as I have right here. Okay, but it depends on where I put it. If I put the 660 all the way up here at the top, okay, then I'm going to get a massive moment, and maybe that moment is too large. If I put the moment down here at the bottom, then I'm not going to have a moment around D at all. Okay, so to get an equivalent system, I want to move it such that I get the same moment, in these two spots. Okay, so the way we do moments in 2D, if you remember, is I'll say like, okay, well, the moment, so in 2D, okay, what is typical, and usually we actually use torque for this equation. So maybe I would say like torque equals moment equals force times distance, right? And this little distance, I like to put this little symbol right here to remind myself that it's a perpendicular distance. Okay. So what we're doing is I know that I've got a 90.6 Newton times meter is my moment, 90.6 Newtons times meters. Okay. And I always put my positive signs, even though they don't have to go there, right? Like mathematically, we don't need to write that. But I usually do because it just reminds me that I'm taking care of that sign. So I kind of just trust myself. Like if I see that plus sign, maybe I'll go back and check it if I've got time on a test or something. But it reminds me like I've already looked into that. I've already checked the sign there. Okay. And then the force is 660 newtons. Okay. And that force is causing, it looks like it's causing a counterclockwise rotation. So the sign on this is correct, is fine. And then we'll go D perpendicular. Okay, so this distance perpendicular, in this case, that's B. That's what we're looking for. Sorry, we should change that to B. Okay, because it said, you know, the distance from the ground to its line of action. Okay, so then this, we just solved this algebraically. Notice that because my units are newtons per meter and divided by newtons, I'm going to get this in meters, not in millimeters, right? So we get 90.6, and I'll divide that by 660. Okay, and I'm left with 0.13727 meters. And since in this class I always want 3 sig figs, 137 millimeters. Okay, I like to go back into the units that were given if I can. Okay, so which means I kind of drew this a little bit too high, which is totally fine. So let's kind of shrink this a little bit. So the equivalent system, okay, if I get rid of all this jibber jabber stuff that I drew on here, okay, is right about here. Okay, a distance like this of 137 millimeters and a 660 Newton force. Okay, so these three systems, 1, 2, and 3 are all equivalent. It just depends on the question, okay, where you stop. Okay, I recommend always going to step 2 before you go to step 3. You could go all the way to step 3 if you wanted to. Yeah, you could. I think it kind of makes things a little bit more difficult if you don't get kind of this single moment at a point first. Now, you don't necessarily have to draw this. Okay? You don't have to draw this if they're just asking for step 3. Any questions? Okay, I find this quite elegant to take this thing right here, you know, or sorry, to take system 1 and replace it with system 3. I find it to be quite elegant.
I have a question.
Yeah.
What's your resultant? Is that the force? Or is it the moment? Or is it
I mean, when I say the word resultant?
Yeah, like in the question.
The resultant of the forces is, yeah, the resultant is usually the force.
That's the 660. That's your resultant?
Yes, yes.
Okay.
Yeah, so I guess we have a resultant force, which is 660. We could have a resultant moment. I don't normally hear people call about a resultant moment. The resultant is the sum of the forces. Whenever I hear moments, I think you usually kind of call it the sum of the moments. But you could call it the resultant of the moments. Anytime you're adding vectors, you can call it a resultant. Yeah, so, but this is, so, yeah. Yeah, the problem is I added this moment. So this is the real way it was written. The resultant of the forces in the distance from the ground to its LOA, but it didn't have this moment right here. But I wanted to make sure that we had an example in class that had a moment. So I just added it in just now.
Yeah, I was just seeing if it was like a combination of the force and the moment or just the force alone.
I'm not 100% sure, to tell you the truth. Let me know if the language ever confuses you again, and we'll figure that out together. Yeah, sorry, that's not a very satisfactory answer. Resultant usually means forces. Okay, so let's try another one. Any other questions? Good question. I apologize for my unsatisfactory answer. Any other questions? All right, let's see here. Clear all drawings. Clear all drawings. Okay, so this next one, I think I got this one off the internet somewhere. Well, I got all these off the internet somewhere. Yeah, I got this one. Here we go. So I didn't print these out for you. Oh, because they're 2D, and I figured I could draw the 2D ones. Next semester, I hope to just like give everybody a a sheet of paper or whatever. And I mean, like a handout at the beginning, like these are all the example problems I'll be doing. But probably next semester will be in person. We're all going to be required to be vaccinated, except for a few of you who have religious exemptions or whatever, or medical exemptions. Okay, so there's some sort of, I don't know, post or whatever they call this thing. Okay, given. I'm going to do given and required because I gave myself too much space here. This is gonna be point A. We'll give these points A. This will be point B. So I'm gonna do this in 2D. So basically, the last one was kind of like a 1D example because all the forces were in the X direction. So I'm just gonna kind of give you another one that's not like that. And the last one we'll do will be in 3D. And I know where to find that one on the internet, so you guys can look at it if my drawing is bad. Don't think my drawings are that terrible, but it is hard to draw in 3D. So I will not be offended if you guys are like, your drawings are hard to follow. That's totally fine. Okay, so then this is 100 pounds. Okay, and this is annoying. You guys may, or maybe it's not annoying to you. For me, I really like it when they give me a 3, 4, 5 triangle, but you can treat this like whatever I like it when they do that. A lot of you will prefer the angle because you'll be like, well, I always just do the same thing with the angle. Okay, so it gives me distances here. Again, I'm going to change these distances. Okay, for the problem, if you were to look this problem up and find it on the internet, it gives 3 feet for each of these. I'm going to give slightly different numbers because you know what, these are fine. We'll do 3 feet, 3 feet, and 3 feet because the distances are going to be 3, 6, and 9, right? Actually, you know what? This really isn't all that different. Let's do this. Let's change this. I'm going to change this problem a little bit. Should have thought of this. I thought I had a nice 2D example, but it turns out that that's really a 1D example. Okay, so then let's have this thing go in a little bend here. Okay, same force, same angle. Okay, 50 pounds. This is also practice with moments, right? Because you guys haven't done that, or maybe some of you have done that homework already. But it's so then this is going to be 3 feet. We're just going to keep everything at let's make that 4 feet. So we'll know so you'll know when we've gone in another direction. Okay, find the equivalent result. So there was the here we go. Find equivalent resultant force and couple, resultant force and couple acting at A. And then, so that's the first type. And then the equivalent single force. Location measured from A and location measured from A. I really doomed myself here. What was this, 200 pounds, 200 pounds. Measured from A. Look, in this case, we're not going to say measured from A. I'm going to say on AD. All right, so we're gonna do exactly what we just did, but we're gonna do it with it's just gonna be a little bit different, right? So now we've got 2D, so I've got to do some forces in the X, some forces in the Y, and then I got to do moments. Okay, and this time we've got two questions. So we want the force and couple acting at A, so they give us the location, and then we get the equivalent single force. And that's going to be, and they tell us it's going to be along AD. If they don't tell you it's going to be along AD, it can be annoying. I don't think they're ever going to do that, but they could. So the first thing I'm going to do, just because it's going to make my life a lot easier, is I'm going to go ahead and get the components of these forces. Okay, I don't think the green shows up very well, so I'm going to do blue. So this force is not in the XY. I mean, it's not. Yeah, it's on an angle. So I want to get its components. Okay. I'm not going to do the trig here. If you want to stay after, we can talk about the trig and do that. But it's going to be 50 sine of 30. I mean, at this point, I'm hoping you guys are getting this. So 50 sine of 30 is this side. So that's going to be 25 pounds. Okay, and the other side is going to be 50 cosine 30. that. Okay, and that's 43.301. 43.301 pounds. Okay. Now for this one right here, we're going to do the same thing. Okay. And sometimes it's just easy to just knock this out early, right? You know, you're going to need this. So just do it, you know. In this case, what I'm going to do is I'm going to do a similar triangle. So I'm going to note we've got 100 pounds along the diagonal. So if I divide by 5, that's 20. And then if I multiply times 4 in the vertical, I'm going to get 80 pounds here. So again, I'm going to take that 100, divide by 5 and get 20 and multiply times 3, and I'm going to get 60 pounds here. Okay, a lot of you will prefer to go and get the angle and then do the trigonometric functions. Okay, I always prefer to use the 3, 4, 5 if I can. Okay, notice this is its own triangle. So like here's the 3, 4, 5. 3, 4, 5. Notice this is a similar triangle. Okay, now these, this is 100, 80, 60. Okay, much easier to just do similar triangles than to do sines and cosines. Okay, so anyway. All right, so now what we're going to do is we're just going to do an equivalent system. Okay, and they gave us a point, so we're going to do this around A. So remember, the forces, it doesn't matter. We're just going to add them up. Okay, so the location doesn't matter for the forces. So some of the forces in the X. Okay, again, I want to write equals 0 because we're already getting used to that. That's not the case here. Okay, so the sum of the forces equals. Okay, I'm just going to expand in the X direction. I've got, let's see, I've got this 60 pound to the right, so it's a positive 60. And then I've got 20 pounds, 25 pounds to the right. Okay, so that's, not too bad, 85 pounds. Okay, let's go ahead and do the Y direction. Okay, it doesn't equal 0. Sorry, it's instinctive. And I'm sure some of you guys are going to get instinctive with that too. You're going to go, oh, equals 0. Okay, it's a hard habit to break. Okay, so let's see here. Some of the forces in the Y, what do they add up to? We've got 200 up. That's positive. We've got 80 down. And we've got 43.301 up. Okay, so the sum of the forces in the Y equals whatever that is. Okay, so 200 minus 80 is 120 plus 140. I don't know why I'm getting out a calculator for this. So wait, so it should be 163.30 pounds. Okay, keeping 5 sig figs all the way to the end. Okay, questions on the forces before I move on? Okay, so let's do the moments. Okay, and again, as always, the moments, in this case, it's the Z direction. If this is X and this is Y, then Z is coming out the board at us, because remember, X is the fingers, Y is the palm, which means the thumb is the Z direction. So the Z is upwards. And if we look at my fingers are curling this way around that point. Okay, and that is going to be the positive. So a lot of times people will draw this to remind themselves of that. Okay, so this is the Z direction, and we're going to take it at A. Most people won't bother saying this is the Z direction. They're just going to say they're taking it at A. I like to remember that it's really going around an axis. Anyway, so again, does not equal 0. Okay, it equals something else. Okay, and again, a lot of people will get into the habit of doing that. It's not really a bad habit. I've never really been in that habit, so I'm going to forget. But it's not a bad habit to get into, to remind yourself, okay, counterclockwise positive, counterclockwise positive. All right, so anyway, so we're going to go, remember, we have to think about all of these forces, okay? And I'm going to kind of like mark them in red as we deal with them. Okay, so here's the 200. Okay, and we've got 200 pounds. Okay, and that's going to cause things to go, it looks like it's going to go counterclockwise, so that's a positive. Okay, and it's moment arms. Remember, the moment arm is perpendicular to the line of action, so that's going to be 3 feet. Okay, then I'm going to do, let's do this 80. Okay, it's going in the opposite direction, but it's got a larger moment arm. So that's going to cause things to spin clockwise. Can you all see which way these things are spinning? Okay, hopefully you can. Please speak up if you can't. Okay, so it's 80 pounds. Okay, because I mean, I'm more than happy to show you. It's just that it kind of like, so relative to A, it's causing things to go this way, right? So if I were to draw a big circle, so that's clockwise, so that'll be negative 80 pounds. And then the distance there, perpendicular distance, is 6 feet. Okay, what about this 60 pounds? What do y'all think?
Doesn't do anything to the
Right.
moment.
Right, because the 60 pound does not have a distance, right? Because so it's acting in the X direction, so I need a distance perpendicular, and that distance is going right through point A. So if I think of point A as my hinge, this thing is just pushing into the hinge. It's not causing the hinge to go either clockwise or counterclockwise. So that 60, we don't even worry about. Okay, so then we're going to go and let's see here. So let's do this 25. And again, remember, it's always nicer when you get your components early. Okay, so then we're not going to have to, we don't have to stop and do a whole bunch of, hold on. Whew. Whew. Excuse me. Yeah, pardon me. Okay, so we'll do this 25. And remember, we want the perpendicular distance. Okay, so this is going to be a 25. Oh, come here. 25 pounds. Okay, and what I'm going to do is I'm going to move it along its line of action like this mentally. I'm going to note, look, here's the perpendicular distance, right? Well, not, oh, sorry, from here all the way down to A, right? So that's perpendicular to the force itself. So that distance is 4 feet. Okay, and it looks like that's going to cause it to go this way, which is clockwise. That's a negative number. Okay.
Okay, so
guys
why do you
Go
use
ahead.
the 25? Why use 25 instead of the 43?
Oh, I'm going to do the 43 too. You need to do both of them.
Oh, okay.
Okay, hopefully you guys are seeing that. We're just going to kind of like walk through this and do them one at a time. So in this case, Jerry and really everybody else, you can do either the 50 or you can do both the 25 and the 43.301. Okay. The problem with doing the 50 is if I did the 50 by itself, I would need to get a perpendicular distance for that force, right? So I'd have to kind of like draw a line like this. And then I have to get the perpendicular. So the perpendicular distance is somewhere like right here, which in this case, I don't want to do that geometry, right? So what I'm going to do instead with that force is I split it into X and Y, because it's relatively easy to get Y distances for my X force and X distances for my Y force. Does that make sense?
Yeah, that makes sense.
Okay. Right. So then we're gonna so then we'll go up and now we'll do the 43. Now we'll do this one. Okay, so it looks like I'm gonna have to go on to the next line because I've used my space poorly. And again, so I'm gonna move it along its line of action until it's at point D. And so we'll get 43.301 pounds. Okay. Its distance is looks like it's 9 feet. Okay, and then let's see, and then so that's causing things to go, looks like it's causing things to go counterclockwise. So that's going to be a positive. Okay, so we add all these up. Sum of the moments around Z at A, around the Z axis at A equals. Okay, so then this is just a calculation thing. So what's this? This is 600. This is minus 480. So we're at 120 minus 100. So we're now at 20. And then, of course, I can't do that last one. 43.3, oh, come on. 43.301 times 9. That big number, 389.71. And we're going to add another 20 to it. Okay, so we get 409.71. 409.71. Okay, and the units here are foot pounds. So we'll do foot pounds. You'll see it written sometimes. Okay, So we've already done part one of this problem. Okay, so part one looks like this. I'm going to just draw it small. Okay, and let's see. So the equivalent system. This is part one. Is 100. So we got 85 in the X. Okay, 163.30 in the Y. Pounds. Okay, and then we need a moment of a positive moment, notice. So it means this is counterclockwise. Of 409.71. Well, since we're reporting, we'll go down to 3 sig figs. So this will be 410. 410 foot-pounds. 401, 410. All right, so. All right, now hopefully what you're thinking is, wait a second, that's not a single force, that's two forces. And you're right. It's actually a single force that we have in components. So what we actually want to do is we actually don't want it like that. So we're going to get rid of that. Okay. So sorry if I messed you around. We actually want a single force. Okay. So we're going to convert those two forces into a single force. Oh, come on. So we're basically going to do Pythagorean theorem. So 85 squared plus 163.30 squared equals, raise that to the half power. Okay, so we're going to get 100. So the resultant of these, F, I guess we could say the sum of F. I don't want to call it sum of F. The resultant, the magnitude is 184.10, 184.10 pounds. Okay, at an angle of, come on, you can draw, thank you. At an angle of, and we'll do the inverse tangent of y over x. So inverse tangent of 163.3 divided by 85. Okay, and we'll get an angle of 62.502. Okay, so basically I would go in here and I would say, okay, well, here we go. It's going up like this. That is an angle of 62.5 degrees, and it is 184 pounds. Okay, any questions?
Sorry, how'd you get the angle?
So what we're imagining is if I take these two forces right here, I'm gonna draw a triangle. Okay, so I've got the X component is 85 pounds. I've got the Y component is 163.30 pounds. So I want this angle. So I said, okay, well, the tangent, so this is theta. Tangent of theta equals the opposite, 163.30 pounds over the adjacent, which is 85 pounds. So then theta equals the inverse tangent of 163. Oh, no, didn't want to do that. 163.30 pounds. Oh no, it froze on me. Oh, it's not showing you what I'm writing. Can you see what it would be the inverse tangent of?
Oh yeah, I see now.
Okay, all right. So this is frozen on me, so I'm gonna have to like.
I still don't understand the part with the 25. Like I feel like a 25 force. I don't know. To me, it looks like that would like rip that off the wall or something.
Well, it's trying to.
Oh, but it can't. So then it rotates.
Right. So basically, it's trying to rotate it, and if the connection at A is not strong enough, it will rip it off the wall. But two things are happening really. So the 25 is causing it to want to rotate like downwards, right? But the 43.301 is causing it to want to rotate upwards. So they're both kind of doing opposite things. The net effect of 43.301 is actually stronger in this case than the 25 because both it's a stronger force and because it has a bigger moment arm.
Okay, I understand.
So what we're going to do when we solve for the reactions is we're going to figure out what the moment at A needs to be in order to keep this thing from rotating.
Hey, Wayne,
Yeah,
real quick question. So just so I can summarize your graph in the top right, your drawing. So is that 410 Newton meters, basically a torque counterclockwise on that point? Is that what that's saying?
410 foot-pounds, but yes.
Foot-pounds basically of torque on that point, and then it's 184 is the result that we're basically going in that degree angle
Yeah, so there's a force of 184 pounds
at
on
62 degrees,
at 62 degrees, right?
but it's causing 410 pounds of torque on that
Right.
point.
Right.
All right, that's all I wanted to clarify.
So if we wanted to keep this thing from turning or moving or whatever, we would need to apply equal and opposite force and moment to keep it there. Okay. So Jerry, that's kind of playing right into your point, right? All of those forces are wanting to really twist it off. And if we want to keep it from twisting off, well, we're going to have to apply a lot of force. We're going to have to apply force at A to keep it where it is. And we're going to have to apply a moment at A to keep it where it is. Okay, does that make sense?
Yeah.
Okay, and then the last bit, of course, and we'll get to this later in the semester, is obviously the beam itself needs to be able to take, be able to handle those kind of forces, right? And so those are called internal forces, and we'll get there.
Wait. So like the one with is that because it's like, I can see the force 100 pounds?
Yeah.
So that one, we only use the Y component for that one because
Right.
it's directly in line. Is that, or how does that part work?
Well, because the X component of that force is going right through the middle of A. So if you have an X component force, you need a perpendicular distance. So imagine this is a door from above, right? So we're looking at the door and you're standing at point C and you're pulling at point C straight away from A. It's not going to cause that door to open or close. It's just going to pull on A, right? It's not necessarily going to go, clockwise or counterclockwise, right? It's not really going to do anything, right? You got to push up or down in order for that door to open or close, right? Does that make sense?
Yeah.
Okay, so that portion of that force is not doing anything.
All right, I see. I was just trying to distinguish between the two.
Yeah, of course. Okay, so well, I'm copying down this answer right here before I move on to the next thing. Because it's not going to let you guys see what I draw unless I clear the whole screen, which is unfortunate. That's what happens when my hand hits the wrong thing. Okay, so I'm gonna go back and I'm gonna do 2 sig figs for the final bit. I'm gonna clear all the drawings because okay, I'm gonna unshare and then share again. Sorry, whenever I do that, it goes haywire. Okay, so we're gonna finish this problem. And so basically we're gonna start from this. All right, and I didn't write down, we're gonna go to only 3 sig figs, which of course is not really the way I prefer it. But I didn't copy down all those numbers, so. Okay, this is 62.5 degrees, and this is 410 foot-pounds. Okay, so now I'm gonna do now I want the answer to part 2. So this was the answer to part 1. And I want the answer to part 2, and it's going to look like this, and it's just going to be a single force, and I want to know where it's going to act, right? And so I already know a few things, right? I already know it's going to be 184 degrees, or 184 pounds, excuse me. Okay, I already know it's going to act at 62.5 degrees. Okay, and to make this even easier, right, I already know the components of that force. You guys are going to have to tell me what they are because I forgot. But I already know the components of this force. This one is 85, I believe. Right, and then there's a vertical component, which was what, 100 and something,
163.3.
163.3.
So, Professor, this is what I find counterintuitive. So, if you move that force along that line, wouldn't it act as a lever?
Yes. So you can think about it this way, right? As we move along the line, so you're saying like we're creating a, it seems like we're creating a, in this case, I guess a counterclockwise moment, correct?
Yeah.
Right, and we are. And so what's happening is as we move along that, as we move that force along to the right, what we're doing is we're creating a counter, right? So
So that moment of 410 at A would increase, or no?
Okay. This 184 needs to account for both the force here and the moment here. So I want this 184 to create this 410. Essentially.
So would that 410 move along with that resultant?
No, hold on. Let me find the answer. And well, no, that's a little okay. So basically, these two systems are. So if I think about point A over here, right, and we haven't found out the point yet. Okay, and I solve this system right here, right? The force on the right is 85. The vertical force is 163.8, and the total moment around point A is 410 foot-pounds. But that moment is coming from this force. Okay, because of the lever arm. Whereas if I do this system over here, that 184 foot-pounds does not contribute to the moment. And it's got 410 foot-pounds that has to be applied.
Ah,
So
okay.
you're trying to find out where on the arm you're causing 410 foot-pounds at part A.
Right,
If you
exactly.
push on, basically I had a wrench, I was pushing it, where would I push on that arm to
Right.
get 410 at the bolt or at A, wherever it is?
Right. Exactly.
Okay.
Okay, so we're going to go ahead and we'll just solve this one. This last little bit is usually very easy. Not always, but the last step is usually the simplest part. And what we're going to do is we're going to ignore this 85, okay, because its line of action goes right through A, so it's not going to cause any rotation. And we're just going to use this 163.3 right here. And we're going to say, okay, well, the moment at A, okay, in the Z direction, okay, equals the force times the distance, okay, that perpendicular distance. And so the moment around Z at A, well, sorry, we know that number. It's a positive 410 foot-pounds equals the force, which is 163.3 pounds. Okay, and then D perpendicular. Okay, and then we'll just solve that equation. Okay, and calculator 410 divided by 163.3, 2 point something. Okay, 2 point, I only use 3 sig figs, so that's all I'm going to answer with. Okay, feet. Okay, so this distance right here is 2.51 feet. Okay, and so that's your answer. Okay, and they're involved. Okay, but I think, if you just walk through it and I forgot who just had that question, Kyle. These, I think it was Kyle. Anyway, these questions definitely got me too. Like I kind of stare at them and I'm like, what's going on here? Why is this? And it is a little bit counterintuitive. And then all of a sudden, when the light goes on, you go, okay, this isn't so hard. Like I can kind of see what it is we're doing here. But I agree with you entirely. It's a little counterintuitive.
One more thing, Wayne. You're using the 163 because that's the perpendicular force.
Right.
Okay.
Right. So if I think about each of these forces in turn, this one, the 163, it's got a perpendicular distance like this. Right. And then this 85, let's use a different color. Okay. It doesn't have a perpendicular distance, right? It just keeps going right into the middle.
Yep, that makes sense. Thank you.
Okay. All right. So I'm going to try to start this 3D one. And maybe I'm just going to set it up. Let me clear all drawings because I'm not going to have a whole heck of a lot of time. Where are my notes? I should start doing the 3D ones earlier. Okay, so this one, if you want to see what this one looks like, you can go to the practice set for moments. And this one will be in, it's number 18, I believe. Anyway, so I'm going to draw this as quickly as I can, which it shouldn't take that long. So we've got, let's see here. Now, some of you have complained to me that you don't like the fact that X and Z and Y are not always the same location. As much
That was with me. Oh my God, that makes me so mad.
And believe me, it wasn't just you. I think I had a few people. And I mean, I hate to be rude like this, but you're gonna have to get over it because that's just, it's going to change. It's gonna be all over the place. But like, for example, this problem, this one even came from your textbook. And I think this is not the way you typically see these. So, I mean, yeah, not trying to be a jerk, but all right, so we've got some kind of thing here. And this is point O. And it's got some sort of, let's see, so up here, there's an axis like this. Okay, and then there's a bar. It's kind of coming off this way.
Which one's I, J, and K in this format?
I is always X, J is always Y, and K is always Z. Always. Okay, you will never see that get altered. And there's like this thing. And there's kind of like an angle going like this. Okay, and here's a P, a force right here. Okay, and this is 15 degrees. Okay, and then they say 134 newtons right here. Okay, this, let's see. This thing is 220 millimeter long, 220 millimeters long. Oh, we get an angle right here.
15 degrees is with respect to the Z-axis.
Right, this is with respect to the Z-axis, this 15 degrees. And yeah, that was the next thing that I was, or basically the X, Z plane, but yeah, the Z-axis, right? Or the negative Z-axis in this case, but whatever. Okay, so what we're going to do is we're going to replace this single force with a force couple system. So this is given and required. Replace force P, or force 134, replace force with equivalent force couple at O. Okay, and I'm not going to even try to draw that one, but I want to show you how to do this. Okay. So the first thing we're going to do is we're going to take this force right here and I want to get it into its components. Okay, so that's annoying, right? So what we're going to do is I'm going to try to go, okay, well, let's see. So we want to put this one thing down to the Z axis. Okay, so we're going to go down like this. Boom. And then we're going to go over like this. Okay, to get those forces. Okay, so the nice thing about this is it really only has two components. It does not have an X component. Okay, that won't always be the case. But this one right here will be 134. It looks like that'll be sine of 15. And this one right here will be 134 cosine of 15. Okay. Go ahead and put those in the calculator and give you some actual numbers. 134 sine of 15. Okay, that's 34.682. 34.682 newtons. And this one down here is 134 cosine 15. Okay, so we get 129.43. Okay. All right. Now, luckily, we do not have to do any more trig with that because we got lucky, right? Because it happened to be parallel to the ZY plane. Okay, so what we'll do now is we'll go ahead and solve this. Okay, so at O, well, we're just going to sum forces, right, in the X direction. Okay, does not equal 0. Okay, I know I keep writing that, it's a little annoying, But we need to remember that. In the X direction, we don't have any forces, so it actually does equal 0. So forget that. Okay, and then the Y direction. Well, there's only one force in the Y direction. Let's see, which one's Y? Y is vertical, so it's this one. So we've got a negative 34.682 newtons. Sweet. Okay, hopefully you guys already know what we would do if we had other forces. But it just turns out in this case, we don't have any other forces, right? So this one's a positive 129.43 newtons. Okay, straight up, easy. Right, now we need to do moments. Now what sucks is, you know, when we're in 3 dimensions, we have 6 equations with some forces in the X, some forces in the Y, some forces in the Z, some of the moments in the X, some of the moments in the Y, some of the moments in the Z. Okay, I don't want to do all of those. So I'm just going to do the single equation. Sum of the moments, oh, put that in the wrong spot. Sum of the moments equals, doesn't equal 0. Okay, so the sum of the moments at O equals. Okay, and this is going to be all of the moments, I, J, K. Good question, right? What is the I and what is the J and what is the K in this case? Okay, and so in this case, the I and the J and the K, this is X, Y, and Z in that order. Okay, so I need the R cross F. Okay, we only have a single force, so there's no reason to play around with multiple forces. Okay, so I already know the IJK of the force, because this is going to be 0 in the X. In the Y, it's negative 34.682. And the K, I'm going to put the units out here just so I don't forget. Well, you know, sometimes I don't write the forces in these things just because the space like that. Okay, now I need to get the R, now I need to get the R. Okay, so wait, how tall is this thing? 100, this is 150 millimeters.
Yeah, you didn't write it down.
Yeah, okay, so we're gonna go from, so I'll do R in blue. R is going from O to here. Okay, it looks like it's opposite of that force, but clearly it's, or maybe not clearly, but it's really not. It's just, you know, it's hard to draw in 3D. Okay, so my Y is the easiest one, 150 millimeters. Okay, because that's how high I had to go. Okay, and now I need to get the X and the X and the Z. So let's do those in like green. All right, so that's that 220. Okay, and I'm gonna like, so here it is right here. And I need to get the 2 sides of this thing, and those are both gonna be in millimeters. This is a right angle right here. So this side is gonna be 220 cosine 35. This is gonna be 220 sine of 35. Okay, and I'm just gonna plug those in. 220 cosine 30, cosine 35. Okay, so that's the X direction, and it's positive. Okay, and so that's going to be 180.21. Okay, I'll get rid of these millimeters because for space concerns. And then 220, sorry, 220, not 222. 220 sine of 35. Okay, 126.19. 126.19. Okay. We're going to cross multiply. I'm just going to go ahead and finish this up. If you need to leave, just go for it.
Wait, so those values, is that like, that's the distance?
Yep.
Oh, the radius, okay. All right,
Yeah.
I'm all right.
R is kind of like a displacement vector. So yes, it's just a distance. Okay, so I'm going to go ahead and copy these over. Negative 34 point. You can do Kramer's rule if you want. I find that to be unnecessarily complex, but you can do that if you want. Okay, so so ideally you're on graph paper, and so these lines make a little bit more sense. But then we'll get some of them not. And what we'll notice here is we're going to get the I, the J, and the K. So we're going to get the X direction, the Y direction, and the Z direction. So here's I. This one, 150 times 150 times 129.43. And I'm going to go ahead and divide by 1,000 because I'm going to do this in Newton meters. So 19.43 415 newtons times meter. We'll do newtons times meters outside everything. Okay, so that's in the I. We'll do J is 0. K is minus. Okay, 34.682 times 0.18021 equals, and we'll get 6.25. 6.2500 in the K. Okay, now we'll do minus. We get nothing in the K from that one. This one becomes, this is a minus sign. It'll be 0.12619 times 34.682. Oh, didn't like it. What didn't like? Oh, it didn't like this thing. Okay, anyway, 0.12619 times 34.682. And this is a 4.3765. Okay, and that is in the I direction. And then here's my J. And that's going to be a plus sign, J. Okay, so let's see here, 0.18021 times 129.43. 23.325. Okay, and all that is units of newtons times meters. So if we combine all of that, let's see, let's put our I's together. So that's 19.415 plus 4.3765. When you're done with your tests, I highly recommend coming back to this and staring and make sure you didn't make sign errors, right? Because this is begging for it. Okay, so this is in the I direction. So it takes care of this one and this one. And then in the J direction, we get a negative 23.325 in the J, and the K direction minus 6.2500 in the K direction. Okay, and all of that is units of newtons times meter. Okay, I can't write meters down there. Okay, so then, you know, the equivalent system, I'm just going to write this in right now because I think, you know, we're over time by 7 minutes now, and I apologize for that. It was important to me that we do a little 3D here. So what we'll end up getting is, if you draw this in 3D, let's draw it on the original. I'm just going to erase the original forces. And so that force is gone. This force is gone. We don't care about any of this. Right? Don't care about this. Boom, right? So now we'll go in, I'll do the force in red. Okay. And so we've got Fy in the Y direction. I mean, I really should draw it as a single force, I guess. Yeah, let's draw it as a single force.
Are you going to post this, Professor?
The recording?
Yeah.
Yeah, I always do. Always.
Why are they always unlimited though?
Record. There was that one time I forgot to hit record. I don't know if that was this class or the other class. So this is that 15 degrees, and I think we decided that this force was 134 newtons. 134 newtons. Okay, so that's the force. Okay, and then the moments, and this is a little bit annoying. Here's the I direction. So here's my X vector. This is my X vector right here. I'm going to put my thumb in that direction. And that means that this is going over the top of that. Okay, so if you put your thumb in the X direction and you wrap your fingers around it, that's the positive direction. So this is 23.8 newtons times meters. Okay, now I'm going to do this, the J direction. Okay, positive in the J direction. If I put my thumb up, positive is going, it looks like it's going around the back. So I guess really we would probably write it more like positive would be over the top, I guess. I guess it depends on how you think of it. Positive would be like this. So we're actually going to go the opposite direction because we have a negative sign. And so it'll be 23.3. Okay. And then for this K, in the Z direction, I'm going to put my thumb going in the direction of Z, and my fingers are going to be curling over the top of that thing. So this thing's actually going to go the opposite direction, which is this direction. And that's going to be 6.25. 6.25 newtons times meters. And we'll talk about more about how to do that. But that would be how, this would be the answer right here. Although I think if you do this in Connect, it's just going to want this answer right here. Okay, I'd prefer you to know what that means though. Anyway, so that's all the time we got. I apologize for running over a little bit. Are there any questions before we sign off?
So the moments don't, the vector is a vector? Or is it like, it's just like a rotation? Is there a rotation on the axis?
It's a rotation vector. So like, let's suppose it's positive I. So what that means is, here's the X direction, here's positive I. So you're going to take your thumb and of your right hand, and you're going to put it in positive X direction. And whichever way your fingers are curling, that's the way that this thing is going. Okay. For J, this is a negative J. So what I can do is I can point my thumb in the negative J direction. Okay. And whichever way my fingers on my right hand are curling, that's the direction I'm going to get. Okay. I've got a negative K. So I'm going to put my finger in my right hand in the negative direction. And whichever way my fingers are curling, that's the direction of the vector.
Okay.
Okay. I mean, it take a little practice to get used to that. And we're going to keep practicing it. So, but like for this is probably a good enough answer, but I would like you to understand what that means.
All right.
Said you're pushing back this week's homework to the 3rd, right? Or something like that.
Sunday.
Sunday?
Yeah, whatever,
Okay.
whatever that date is.
Okay. Also, why did you write IJK and then IJ on that sigma M initial or whatever? When you did the R
Right here.
Yeah, the Kramer's rule. No, above that. When you did the Kramer's rule, why did you write IJK and then another IJ?
Well, this is just one of the ways to calculate the determinant of a 3x3 matrix. You just you basically expand it, because basically what I'm doing is I'm going on these diagonals, and really this one right here goes down here and then crosses over to here. So I didn't feel like doing this over to here, or K goes like this and then goes down through here, but that's just annoying to write it that way. So this is how I do it. If you want to do the Kramer's rule, you can do that. But it's just the way you calculate a determinant. I can go over it again next class if you like.
Yeah, okay. That was really weird to me. I was like, because like when Jeff does his, he just does it like normal way, and then you were also doing normal. Huh?
When who does it?
Jeff Hansen, when he does it. So
he does a Kramer's rule. If you want to use Kramer's rule, where you just cover up the I and then do the cross product of the smaller matrix, you can do it that way if you want. I find that to be more rife with problems, but whatever works for you.
Okay, bye-bye.
Okay. All right, I'll see you guys. And I actually got to run. Let's see here. It's